Can something truly come from nothing? Or are we bound by an eternal truth? Nothing is created and nothing is destroyed, only transformed? This idea, the law of energy conservation, is one of the cornerstones of modern physics. It's a principle so fundamental that it underpins everything from the motion of planets to the tiniest interactions of particles. But is it as universal as we think? What if this sacred law is not an unshakable truth, but a mere convenience, a framework we use to understand a world far more complex than we can imagine? Today we'll dive deep into the origins, limitations, and controversies surrounding the law of energy conservation. Get ready to question everything you thought you knew. Energy is often described as the capacity to do work, but what does that actually mean? Imagine pushing a car up a hill. That's work. The ability to push that car, whether it comes from your muscles, a gas engine, or an electric motor, is energy. It's the invisible force driving everything we see in the universe, from the wind blowing through trees to the dazzling energy of the sun itself. But here's the catch. Energy isn't something you can touch, hold, or directly observe. It's not like matter, which has mass and takes up space. Instead, energy is an abstract concept, a way for us to measure the ability of a system to cause change or motion. It's deeply intertwined with forces, motion, and interactions, but at its core, energy is a human invention, a mathematical tool designed to help us understand the workings of nature. So, is energy real? Or is it just a convenient story we tell ourselves to make sense of the universe? Keep that question in mind as we move forward. Think of energy like money in a bank account. You can withdraw it, deposit it, or transfer it between accounts. For example, when you eat food, your body deposits that chemical energy into muscles. When you run, it withdraws that energy and converts it into motion. The total balance, the amount of energy, remains constant, much like a financial budget. But here's where it gets tricky. Just as money is not an intrinsic property of the physical world, but a construct we've created to facilitate trade, energy might not be an absolute property of the universe. It's a system of accounting that allows us to track changes and predict outcomes. This idea raises profound questions. If energy is just a bookkeeping tool, does that mean it's not fundamental to the fabric of reality? And if so, what does this say about our understanding of the universe? As we'll see, the answer isn't as straightforward as it seems. For centuries, scientists categorized energy into neat boxes: kinetic energy for motion, potential energy for stored forces, thermal energy for heat, and so on. It was a simple, elegant system that explained most phenomena. But as we delved deeper into the universe, these categories began to blur. Take dark energy, for example. It's a mysterious force that makes up about 68% of the universe, driving its accelerated expansion. It doesn't fit into any of the classical categories. Its discovery forced scientists to reconsider the very nature of energy. And then there's the question of whether these types of energy are truly distinct or merely different manifestations of a deeper, unified phenomenon. Could energy itself be an emergent property, something that arises from more fundamental principles we have yet to discover? The more we learn, the less we seem to know. For much of history, scientists believed that the universe could be explained using just two types of energy: kinetic, the energy of motion, and potential, the energy of position. A pendulum swinging back and forth seemed to perfectly demonstrate this balance. But real-world systems are rarely that simple. Over time, energy leaks out of the pendulum in the form of heat due to friction. Where does that fit into the picture? And what about systems like quantum fields, where energy doesn't behave in classical ways? This oversimplified view of kinetic and potential energy is useful, but it falls short of capturing the complexities of the universe. It's like trying to describe a symphony using only two notes. There's so much more happening beneath the surface. Energy is not an absolute quantity. It depends on your point of view, or what physicists call the reference frame. For example, a ball sitting on a train, moving at 100 kilometers per hour, has no kinetic energy from the train's perspective, but it does from the ground's perspective. Now add control volumes, imaginary boundaries we draw to calculate energy in a system, and things get even more complicated. The energy of a system can appear to change depending on where we draw the line. This fluidity shows that energy is a relative concept, not a universal constant. It's a reminder that our understanding of energy is shaped as much by our tools and perspectives as by the universe itself. The idea of energy didn't appear overnight. It took centuries of debate and experimentation to emerge. At the heart of this journey were two brilliant minds, Isaac Newton and Gottfried Wilhelm Leibniz. Newton focused on momentum, a straightforward concept defined as the product of mass and velocity. It was a practical tool for predicting the motion of objects, from apples falling to planets orbiting the sun. But momentum alone couldn't fully explain certain phenomena. Leibniz, on the other hand, proposed the concept of vis viva, or living force. He argued that the true measure of motion wasn't just velocity, but velocity squared. This idea laid the groundwork for what we now call kinetic energy. At first, Newton's perspective dominated, but over time, the scientific community began to recognize the value of Leibniz's insights. Together, their work set the stage for the modern understanding of energy. It's a reminder that even the most fundamental concepts are built on layers of debate, refinement, and discovery. While Newton and Leibniz laid the foundation, it was Emilie du Chatelet who truly cemented the idea of kinetic energy. An 18th century French mathematician and physicist, du Chatelet was one of the few women in science at the time, and her contributions were groundbreaking. She conducted experiments that involved dropping weights into soft clay and measuring the resulting impact. Her findings demonstrated that the depth of the impact was proportional to the square of the velocity of the weight. This proved Leibniz's theory of vis viva and challenged the prevailing notions of motion and energy. Du Chatelet's work not only advanced the understanding of energy, but also highlighted the importance of experimental evidence in shaping scientific theories. Her story is a testament to the power of curiosity and determination in the face of societal barriers. Fast forward to the early 20th century, and we meet Emmy Noether, a mathematician whose work changed the course of physics forever. Noether's theorem revealed a profound connection between symmetries in nature and conservation laws. For example, the conservation of energy arises because the laws of physics don't change over time. This might sound abstract, but it's incredibly powerful. It means that energy conservation isn't a fundamental truth of the universe. It's a consequence of how the universe behaves. Noether's insights also open the door to new questions. If symmetries in nature were different, would energy conservation still hold? And if energy conservation depends on symmetry, what happens in systems, like the expanding universe, where symmetry breaks down? Her work reminds us that even the most sacred laws of physics are not untouchable truths, but reflections of deeper principles. In classical physics, energy conservation feels like a law written in stone. But as we dive into the realms of quantum mechanics and cosmology, cracks begin to appear. In quantum mechanics, particles can seemingly appear and disappear, creating what's known as quantum fluctuations. These phenomena don't fit neatly into the framework of energy conservation as we understand it. In cosmology, the universe's expansion adds another layer of complexity. As space itself stretches, energy doesn't remain constant in the traditional sense. For instance, the energy density of light decreases over time, challenging the idea of a fixed total energy in the cosmos. These examples show that energy conservation isn't as universal as we once thought. It works beautifully in most everyday scenarios, but at the extremes of reality, at the smallest scales and largest distances, it starts to break down. Does this mean energy conservation is a myth? Not quite. It's more like a useful approximation, a tool that works in most cases but has its limits. And those limits are where the most exciting discoveries happen. So is the law of energy conservation a myth? The answer is both yes and no. It's one of the most reliable tools in physics, a guiding principle that has shaped our understanding of the universe. But it's not the whole story. Energy conservation, like so many scientific laws, is a reflection of the patterns and symmetries we've observed in nature. It's not an unbreakable rule, but a remarkable insight into how the universe works, most of the time. In the end, this journey through energy conservation teaches us a valuable lesson. Nothing in science is as it seems. The universe is more complex, more mysterious, and more surprising than we can ever fully comprehend. And that's what makes it so beautiful. Ending screen. Thanks for watching. Don't forget to like, comment, and subscribe for more mind-blowing science.